Hi and welcome to this last lecture of module 4. In module 4 we were so far we were discussing about getting solutions to nonlinear equations, the nonlinear equations in general of the type fx equal to 0, and we looked at several methods to get the solutions for a single variable case, and in the previous lecture we extended it to multivariable case where we had several functions of several different variables and trying to find out all the values of those x1 to xn that satisfy the equation f1 equal to 0, f2 equal to 0 up to fn equal to 0. Specifically we looked at the fixed point iteration method and the Newton-Raphson's method, and in the last I guess 20 minutes or so we just covered some of the extensions to the Newton-Raphson's method that are useful in making the method either more accurate or more applicable in some sense. So that is what we have been talking about so far, f of x equal to 0. There is another type of problems of the same sort, f of x equal to 0, where f of x is a polynomial function. Root finding for polynomial functions. Okay. What I have done over here, I have listed just 3 particular examples of polynomials. The first one is x cube minus 7x plus 6. You can write this as x cube minus 6x minus x plus 1, and then you can do a very straightforward algebraic manipulation on that, and you will essentially get this particular polynomial factored as x minus 1, x minus 2 and x plus 3, product of these 3 terms. If we call this as f1 of x equal to 0, then the x values that satisfy f1 of x are going to be x equal to 1, x equal to 2 and x equal to minus 3. Okay. So this particular guy is going to become 0 when either this term or this term or this term becomes 0. The difference is, now given any arbitrary polynomial, what we want to do is to find out all the roots of that particular polynomial. What I have also listed over here are 2 other polynomials, and again of the third order. So what are the roots of the 3 polynomials? The roots for the first polynomial are x equal to 1, x equal to 2 and x equal to minus 3, as we had listed earlier. The roots of the second polynomial are x equal to 1, the second root is again x equal to 1, and the third root is x equal to minus 3. So x equal to 1, 1 minus 3, and for the third polynomial, if we look at, it's x square plus 1 equal to 0, so x square equal to minus 1 or x equal to plus or minus I. So the 3 roots are x equal to I is the complex constant, x equal to minus I, and the third is x equal to 3. Okay. So the point of view listing these 3 polynomials was this: any polynomial of nth order, for any nth order polynomial okay, an nth order polynomial will have, or sorry, exactly n roots. Okay, for example, all of these third order polynomials have 3 roots. Okay, some of the roots may be repeated. Okay, it's not necessary that all the n roots have to be unique roots. Okay, in the first example we got 3 unique roots, 1, 2 and minus 3. However, in the second example we got repeated roots, so 1 and 1 are actually repeated roots. There may be repeated roots, may or may not be Okay, and the final point is that the roots could be complex numbers as well. In this particular case we get a purely imaginary number, in some other cases we might actually get complex numbers also. So the third point is complex roots are possible. Okay. So what we have is, when we have an nth order polynomial, we are interested in finding all the n roots of that polynomial, if even if those roots end up being complex numbers, or even if those roots are repeated roots. So we will start Newton-Raphson's for polynomial root finding. Okay. So what we will do is, we will start off with certain initial guess x1, okay, and use Newton-Raphson's method to get the actual root. Let us call it x bar 1, just to represent that it is one of the roots of that particular polynomial. So let us say we look at again the first polynomial x minus 1 multiplied by x minus 2 multiplied by x plus 3, and essentially if we start off with that particular polynomial, perhaps for that polynomial the curve perhaps is going to look, so we have intersection at minus 3 plus 1 and plus 2 for negative values of x. For very large negative values of x, the function f is going to be very highly negative. So perhaps I think, if I have to guess, this curve is, maybe the curve is going to look somewhat like this. Okay, I'm just drawing a cartoon, I don't mean the curve to be exactly in this form. Okay, so the three roots are minus 3 plus 1 and plus 2. Okay, these are the three roots, and what we are interested in doing is, we are interested in finding out all these three roots of this particular equation. Okay, so let us say we start with our x1 at this particular value. Let's because we don't know, assuming we don't know anything about this particular equation, let us start with x equal to 0 as the initial guess. If we start with x equal to 0 using Newton-Raphson's method, we will first get our x1 bar equal to 1. So we started off with a polynomial of the form x cube minus 7x plus 6. From x cube minus 7x plus 6, we found one of the polynomials was x bar equal to 1, sorry, one of the roots was x bar equal to 1. So what does that mean? That just means that x minus 1 is a factor. Okay. So x minus 1 is a factor of x cube minus 7x plus 6. So what we can then do is divide essentially x cube minus 7x plus 6 by x minus 1, and if we do that, x cube minus 7x divided by x minus 1, basically what we should be getting is x minus 2 multiplied by x plus 3. So this should essentially lead us to x square plus x minus 6. Okay. So we started with a polynomial of third order. We used the Newton-Raphson's method to find out one of the roots of that polynomial. Once we found out that root, we divided the original polynomial with the with x minus the root that we have found, and we got a polynomial of one order lower. So we started with, let's call all our polynomials, let's represent them as p subscript n, which represents, n represents the order of the polynomial, p represents that it's a polynomial. When the first root is found, when the root x1 bar is found, the polynomial, then we can what is known as deflating the polynomial. The polynomial can be deflated to Pn minus 1. Okay. So I will write that over here. Pn is going to be equal to Pn minus 1 multiplied by x minus x1 bar. The curve x square minus x plus 6 perhaps would look let us see. Okay. So this was our P1, this became our P2. Okay. Now in the polynomial, sorry, this was our P3, from P3 we went to P2 after deflating out the polynomial x, after deflating out the factor x minus 1. So now this particular curve now intersects the x axis at 2 points, minus 3 and plus 2. What we can essentially do is we can start again with our Newton-Raphson's method with our x1 bar equal to the previous solution. So we can start off our x1 bar at this particular value, okay, and then use Newton-Raphson's method. Perhaps we will go this way, this way, this way and so on, and we will end up at the solution 2. So what has happened is we first from Pn minus 1 we obtained x1 bar, deflated that particular expression to from Pn, we deflated that expression to Pn minus 1. From Pn minus 1 we got our second solution x2 bar and deflated it to Pn minus 2, and we repeat this until we reach P1. Okay. Each time we get a solution, we deflate the overall polynomial. By deflating I mean nothing but removing that particular factor from that the original polynomial that we started off with. Okay. So I will just write down the algorithmic steps that we are going to follow in this particular case. Is we start with Pn. The second part is choose initial guess, x1 and subscript 1 to represent that we are trying to find the first root of that particular polynomial. Use Newton-Raphson's to get the first root, or in general, yeah, x1 bar. Okay, so we will use the Newton-Raphson's to get the first root x1 bar, deflate polynomial to get P n minus 1, okay, and then essentially repeat this step, the steps from 2 onwards, repeat the steps until we get all the solutions, okay. And when we are actually going to repeat the steps, at that time we will choose the initial guess x2 1, we will get Newton-Raphson's to get the second root x2 bar, deflate the polynomial to get Pn minus 2 and keep repeating over and over again. So I will use, instead of 1 and 2 and 3, I will just use I over here to indicate the ith root, okay, and we will repeat this until we get the polynomial P1. The question happens is, what if we do not have real roots but we have complex conjugate roots? But going back to what we discussed in the previous lecture, improvements to Newton-Raphson's method in case of multiple roots, we had said that improvement to the Newton-Raphson's method would be xi plus 1 is going to be equal to xi minus m times f of xi divided by f dash of xi. So this was what we said was Ralston's improvement to if there are m repeated roots, okay. Now in the polynomial of Pn, whenever we have a polynomial of Pn, there are n repeated roots, which of course means we will replace this m by n. When we deflate that polynomial to Pn minus 1, instead of this expression we will use n minus 1 multiplied by f divided by f dash. When the polynomial becomes Pn minus 2, we will use this as n minus 2 f divided by f dash, where of course f is going to be replaced by Pn, Pn minus 1, Pn minus 2 and so on, and f dash is going to be nothing but the first derivative of the specific polynomials. Okay. So this is the procedure we can actually follow in step number 3. So the Ralston's modification is something that we can use in step number 3 in order to get faster convergence of the Newton-Raphson's method for multiple roots. This is because we know a priori that a polynomial of the form Pn has n roots, and we are interested in finding out the n roots of that particular polynomial, and every time we deflate the polynomial, the number of roots decreases by 1. Okay. So that is basically the background of using a Newton-Raphson's method directly to polynomials. Now the question is this the best that we can do, especially when we have when we have complex roots, and in case of complex roots there is indeed a better method to use, and we will go back to what to the expressions that we had, and we will just look at this particular expression where we would get complex roots. So what we got was there was one real root x equal to 3, and there were two complex roots x equal to I and x equal to minus I. Okay. The complex root will for all the real coefficients, we know that they always come in complex conjugate pairs. Okay. And so if we have one complex root is say a plus ib, then we are sure to have another complex root a minus ib. Okay. We are definitely going to have, if a plus ib is a complex root, a minus ib is also going to be a root of that particular equation, and then if you multiply the two roots x minus a minus ib multiplied by x minus a plus ib, when we multiply these guys, essentially we will get this essentially in the form, let us say x square plus px plus q. Okay, where p and q are real numbers. What we are going to do in our new method is basically deflate the polynomial by from Pn to Pn minus 2, from Pn minus 2 to Pn minus 4, and so on until either you are left with P1 or you are left with P2. You will be left with P1 if the order of the polynomial is an odd order. We will be left with P2 if the polynomial order is an even order. Okay. So let's go forward and look at what we can do, and this is going to form the basis of the Bairstow's method for root finding. Okay, and the Bairstow's method for root finding is the first part of it is going to be as follows. Let us say any polynomial Pn, let us represent that as a0 plus a1x plus a2x squared plus a3x cube plus so on up to an x to the power n. Okay. let q equal to x square plus px plus q be one particular second order polynomial. Okay. What we are interested in finding out is whether this particular guy q, whether or not it is a factor of Pn. Okay. So any polynomial Pn can be written as a product Pn minus 2 multiplied by q. If q is a factor, then this is what we will be able to write. For example, in this particular case, x square plus 1 was a factor of this particular polynomial, so we could write p3 equal to q multiplied by p1. Okay. If we do not have x square plus 1, but we have certain other polynomial, we will not be able to write it in this particular form, but there will be a remainder r. Okay. This is exactly how we write any number, a divided by b, if that is equal to some coefficient p and some remainder r, we will write a equal to p multiplied by b plus r, and that is essentially what we are writing. Only difference is this is for a polynomial function. Okay. So now Pn minus 2, we will be able to write that as b0 plus b1x plus b2x squared and so on up to bn minus 2 x to the power n minus 2. Okay. And let us write r as nothing but c0 plus c1x. Okay. So Pn minus 2 multiplied by q is going to be nothing but b0 plus b1x plus b2x squared plus so on up to bn minus n minus 2 x to the power n minus 2 multiplied by x square plus px plus q, which we would be able to write this as x square b0 plus b1 x cube plus b2 x to the power 4 and so on up to say bn minus 3 x to the power n minus 1 plus bn minus 2 x to the power n. Okay. So this is when we multiply x square with this plus multiplying px with this particular term, we will get b0 px plus b1 p x square plus b2 p x cube plus b3 p x to the power 4 and so on up to bn minus 2 x to the power n minus 1. Okay. This is bn minus 2 multiplied by x to the power n minus 2 multiplied by p multiplied by x will give us bn minus 2 multiplied by p multiplied by x to the power n minus 1. Okay, I am sorry, I missed a p over here. Okay. And then we multiply q with all of this, and so we will have b0 q plus b1 q b1 q x plus b2 q x square plus b3 q x cube plus so on up, and there will not be an xn minus 1 term over here. We will end up with p b n minus 2 multiplied by x to the power n minus 2 term. Okay. So when we add all these guys up, we can collect the terms in x to the power n, collect the terms in x to the power n minus 1 and so on and so forth, and equate them to the original polynomial that we had. Okay. So this is our Pn minus 2 multiplied by q. What I will do is I will actually erase this part for now. Okay. And r we will write this as equal to c0 plus c1x. Okay. And when we add all these terms up, when we add all these terms, we should essentially get this. Now what we will do is we will start at the other end at the nth power of this particular term and start moving towards towards the lower powers. So bn minus 2 x to the power n, and then we have an x to the power n. These have to be equal. For this to be for these two things to be equal, essentially every coefficient of x to the power 1, x to the power 2, x to the power 3 and so on up to x to the power n should be equal to the original coefficients, which gives us essentially bn minus 2 is going to be equal to an. Okay. Then the second expression for this is for x to the power n term, x to the power n minus 1 term is bn minus 3 multiplied by p times bn minus 2 plus p bn minus 2 equal to an minus 1, which will give us bn minus 3 equal to an minus 1 minus p times bn minus 2. For any ith term, okay, if we look at this particular thing, for any x to the power ith term, what we will get for x to the power I, we will get b I minus 2 plus p times b I minus 1 plus q times bi is going to be equal to ai. Okay. And at this point of time we know bi, we will know bi minus 1, we will not know bi minus 2. So we will be able to write bi minus 2 is equal to ai minus p bi minus 1, or rather we will write this as minus q b I minus p b I minus 1. Okay. So for n we will have bn, for n we will have bn minus 2 equal to an, for n minus 1 we will have bn minus 3 equal to an minus 1, an minus an, sorry, for bn minus 2 we will have n minus 3 we will have an minus 1 minus q times bn my n, so by n minus 1, but bn minus 1 does not exist, so this particular guy will vanish away and we will just have p times bn minus 2. Okay. So writing those out all together, what we will essentially get is bn minus 2 equal to an, bn minus 1 equal to an minus 1 minus pbn minus 2 and bi is just going to be equal, so bi minus 2 is just going to be equal to ai minus qbi minus pbi minus 1. We will repeat this essentially until we reach b1. When we actually reach b1 at that time, until we actually reach the x to the power 2 power, when we reach x to the power 2 we will essentially get our b0. Okay. Once we get the b0, our objective is to find c1 and c1 and c0, and c1 we can get with respect from basically the first powers, and c0 will get with respect to the 0th power. So c1 plus b0p plus b1q equal to a1. So we will get c1 plus, so we have c1 plus b0p plus q b1q equal to a0. So we take all these terms on to the left hand side and we will get basically C1 as A0 minus B0P minus B1Q, that is going to be our C1, and our C0 is going to be, so C0 plus B0Q equal to A0, so A0 minus B0Q is going to be our C0, this I am sorry should be A1, okay, and this I essentially I goes from basically from we are going from x to the power n minus 2 from n minus, so bi minus 2 is essentially going from n minus 2 to 0, okay, or in other words I goes essentially from n to 2. And this is essentially what we will get, okay. So the idea behind this is that you start off essentially with assuming P and Q, okay. Once you assume the value of P and Q, we basically deflate the polynomial to get P n minus 1 and Q, sorry, P n minus 1 and R. Check if R equal to 0, or in other words C0 equal to 0 and C1 equal to 0. If not, we run Newton-Raphson's to get C0 as a function of PQ equal to 0 and C1 as a function of PQ equal to 0, okay. And the value of P and Q that will give C0 equal to 0 and C1 equal to 0 is the root for that particular equation, okay. So this is the procedure that we will essentially follow in order to get the roots of the particular polynomial, and we will follow this particular procedure repeatedly until we get the entire polynomial deflated from Pn to Pn minus 2, Pn minus 2 to Pn minus 4 and so on up to P0, okay. So what we will do next is just basically take one particular example and just go through that example to see how this deflation is going to work. Okay, so now that we have looked at various solution techniques, what I will just do is just go ahead and summarize the overall contents of module 4, and the summary what we did essentially in the nonlinear equation solving is we started off with the bracketing methods, looked at bisection and Regulus-Folsi methods, and then looked at open methods, secant, fixed point iteration and Newton-Raphson's method, and then looked at extension of fixed point and Newton-Raphson's iterations to multivariable systems and modifications essentially to Newton-Raphson's method to improve the Newton-Raphson's method. So that is essentially what we have covered, and then we covered the root finding methods, and in root finding essentially what we started off with saying is there is a possibility of using the Newton-Raphson's method in order to find the roots of an equation, and every time we find the roots we go ahead and deflate the overall polynomial, and we keep repeating that over and over again, okay. So that is what the overall outline. Coming back to the summary, first we will summarize the overall nonlinear equation solving methods. It is all the equation solving methods that we looked at essentially were iterative methods. So this is the overall algorithm that we had seen pictorially for this particular example. We start with an initial guess that is shown by this red dot over here, and then we use a chosen strategy to move this red dot to the next point. At this next point we verify if the stopping criterion is satisfied. In this particular case the stopping criterion is not satisfied, so we go back, use this chosen strategy to move in the direction of the solution, and we do that repeatedly until the stopping criterion gets satisfied. When it does, we have the solution that is available. We have looked at 5 different methods for us given xi and xi minus 1, or how to go on to find xi plus 1. And I have summarized this in the table. So the 5 methods that we looked at: bisection, reguli falsi. Reguli falsi is also known as method of false position, fixed point iteration, which is also known as successive iteration or successive substitution method, then the secant method, and then finally the Newton-Raphson's method. The bisection method starts with 2 initial guesses. Reguli falsi also starts with 2 initial guesses. These 2 methods are bracketing methods. Because they are bracketing methods, the 2 initial guesses have to lie on either side of the solution. When it comes to a fixed point iteration, when it comes to a secant, when it comes to fixed point iteration, and when it comes to Newton-Raphson's method, we only need 1 initial guess, whereas in secant method we need 2 initial guesses. Strictly speaking, in secant's method we do not need the 2 initial guesses to fall on either side of the solution. We can start with 2 arbitrarily chosen initial guesses also. Okay. And xi plus 1, this is how we move from the current guess to the new guess xi plus 1. In bisection is nothing but midpoint of the 2 solutions xl and xr. In case of reguli falsi and in case of secant method, we join the line connecting the point x comma f at xl and x comma f at xr, and find where that straight line intersects the x axis. As a result of this, both these 2 expressions, both these 2 methods have the same expression. The only difference in reguli falsi is we retain the solution such that one solution is to the left hand side of the true solution, then the other solution is to the right hand side of the true solution, whereas in secant method we only keep the solution, the ith solution and the I minus 1 solution, only the latest 2 solutions. Okay. The fixed point iteration we use xi plus 1 equal to g of xi, and in Newton-Raphson's method xi plus 1 is xi minus f divided by f dash computed at xi. We also looked at the order of convergence, we also looked at the order of convergence. Bisection method was first order convergence, fixed point iteration also was first order convergence, first order method, and Newton-Raphson's method we saw was the second order, has a second order, a quadratic rate of convergence. We did not derive the rate of convergence for reguli falsi or for secant method. Reguli falsi and secant method have a superlinear rate of convergence. That means in the expression ei plus 1 equal to ei to the power eta, eta is a value that lies between 1 and 2. Typically it lies very close to the golden section rules, golden section. In general you can expect in the reguli falsi method to the order of convergence to be anywhere between say 1.4 to about 1.6. That is what the reguli falsi ends up being. For secant it is equal to the golden section. Okay. Then stability, given the 2 initial guesses are feasible initial guesses, the bracketing methods are guaranteed to be stable, whereas the open methods, as we have seen, there is no guarantees on stability of the open methods. In fixed point iteration method we looked at a numerical example where the fixed point iteration does not converge. Although we did not look at numerical examples for secant and Newton's that does not converge, we really motivated these 2 examples using some kind of a graphical method to say under what conditions these methods are not going to converge. Now the issues, the important issues with respect to all of these methods is that bisection and reguli falsi are essentially single variable methods, and we have to ensure that f of x changes the sign at x bar. So for example, an equation of the sort f of x equal to x square, you cannot use bisection method because we will not be able to find xl and xr which satisfy f of xl multiplied by f of xr equal to less than 0. That is because if f of x is equal to x square, the f of x is always going to be positive no matter what value of f of x we use. Okay. The fixed point iteration, the applicability is limited because of stability issues. We saw that this conditions for stability of fixed point iteration were fairly stringent conditions for stability. The secant method and the Newton-Raphson's method are both very versatile and very fast methods, specifically the Newton-Raphson's method. It is a very versatile method, and the reason for popularity of Newton-Raphson's method is one, because it is extendable to multivariable systems. Second, because when f dash of x is not available, we can actually use a numerical derivative, and when we use a numerical derivative, the Newton-Raphson's method kind of resembles a modified secant method in some ways. And the overall requirement is that the Newton-Raphson's method should not have f dash of x equal to 0. If f dash of x equal to 0, then the Newton-Raphson's method cannot continue. So a requirement for Newton-Raphson's method to continue is that f prime should be not equal to 0. And likewise, we should start with an initial guess which is not far away from the 2 solution x bar, and it is applicable to multivariable system, and that is the reason why Newton-Raphson's is what we considered for multivariable system, as well as we considered the fixed point iteration for multivariable system. So the extension to multivariable system for fixed point iteration we saw was straightforward. It kind of follows the same idea that we used in the Jacobi iteration. So when we have the equations x bar f of x bar equal to 0, all we need to do is essentially x of I plus 1 should be equal to, there is a typographical error over here, this should actually be g and not f. So to keep up with really the previous notations. So x of I plus 1 should be equal to g bar of xi, and this is what we need to iterate on over and over again in order to get until we converge when we are going to use fixed point iteration. We saw that the sufficient condition for convergence is that the absolute values of the sum of the absolute values of partial derivatives of the function with respect to x1, x2 and so on up to xn should be less than or equal to 1. Okay, this is the condition for convergence, and I had stated without actually proving or without actually looking at the examples that this often ends up being a fairly stringent condition for fixed point iteration, which limits actually the applicability of the fixed point iteration method. Okay, and then we looked at the multivariable Newton-Raphson's method, and the multivariable Newton-Raphson's method is xi plus 1 is xi minus j inverse f, where j is nothing but Jacobian, and this is how the Jacobian is written, df1 by dx1, df1 by dx2 and so on up to df1 by dxn, and on the column we have df1 by dx1, df2 by dx1 and so on up to dfn by dxn. So we essentially get this square matrix. These values have to be computed at the guess x bar at I, and we substitute that over here, we multiply that with the function value computed at x of I, and this is the iterative equation that we will get. The Newton-Raphson's multivariable method also has a quadratic rate of convergence, and then what we looked at is certain improvements that have been developed to improve the speed of convergence or to improve the stability of the Newton-Raphson's method. Okay, so the Ralston's modification, and this is something that we considered in this lecture also, the Ralston's modification, if there are m roots, is that instead of having xi plus 1 equal to xi minus f divided by f dash. Instead of that, we multiply this with a factor m. Another improved Newton-Raphson's method based on the Ralston's modification we said was, if we write h of x equal to f divided by f prime, the roots of f of x are going to be the same as the roots of h of x. So all the roots of f of x will also appear as roots of h of x, and based on that we obtained a modified Newton-Raphson's formula. In fact, if we rigorously derive this particular formula, we will notice that this is a third order accurate formula. So we can actually improve the accuracy of the Newton-Raphson's method from a second order accurate to a third order accurate method. The pitfall or on the flip side for this particular method is, not only do we need to calculate f prime, we also need to calculate f double prime in order for this particular Newton-Raphson's the third order Newton-Raphson's method or the improved Newton-Raphson's method to work. Okay. The other modification, so these modifications were for multiple roots and especially to speed up the Newton-Raphson's method for multiple roots. More importantly are the modifications that ensure stability of the Newton-Raphson's method. And one of the biggest or two major problems that we had seen with Newton-Raphson's method is, one is when f prime of x becomes equal to 0, and the other case is when cyclically we keep repeating the same roots. So that means the root xi sends us to xi plus 1, and then xi plus 1 sends us back to xi. So xi plus 2 equal to xi, xi equal to xi minus 2, xi minus 2 equal to xi minus 4, so on and so forth. So we will not get convergence, we will keep circling around the actual x bar. That is also a fairly common problem in Newton-Raphson's method. So a straightforward way of modifying the Newton-Raphson's method is what is known as a line search algorithm, and line search is very much like the Jacobi over relaxation or the Jacobi under relaxation that we had looked at. The only difference is, instead of using a Jacobi type of an iteration, we use that under relaxation factor in the Newton's iteration. So instead of having xi plus 1 equal to xi minus j inverse f, we have xi minus omega j inverse f, where omega is a value between 0 and 1, and that is an under relaxation parameter. So what we are saying is, we are going to take really smaller steps than what Newton-Raphson asks us to take, just to be a bit more conservative in tracking the solution. This will reduce the speed of approach to the solution. This is definitely going to reduce the speed of approach because of the under relaxation, but it will improve the stability of this solution. And there are various ways to get a good under relaxation parameter. These ways we are not covered in this particular lecture, and there would be suggested further readings if you are interested in knowing how to get this under relaxation factor. And then finally we also looked at a Leeuwenberg-Marquardt modification to the Newton-Raphson's method. Technically speaking, the LM method actually really comes in the optimization and finding out essentially a least square minimization. If you do not understand the terms, do not worry about it. The motivation behind this is that the roots of the function f of x are nothing but the minima of f square of x. We saw that essentially two lectures earlier what that means pictorially, and when we use this Leeuwenberg-Marquardt's modification, instead of having j inverse f, instead of that we will have j transpose j plus beta I, where beta is a very small factor inverse j transpose f. This is how to get the beta, and all that are fairly advanced techniques which you need to do further reading on in order to figure those things out. And in today's lecture, what we looked at is the Bairstow's method for root finding. We actually did not go into the meat of the Bairstow's method because that would essentially involve a fair amount of basically it will involve fair amount of algebraic manipulations, which I think you can you will now be very well equipped to go and read up any of the textbooks to understand that. So that's why essentially for the lack of time we didn't go into that, but the idea is that any nth order polynomial can be written as a product of n minus 2 order polynomial and a quadratic polynomial plus a remainder r. When the remainder r equals 0, at that time q is a factor of p. For example, in the examples that we had looked at, for example in this particular case, x square minus 1 is going to be a factor of this particular expression. So if we choose the value of p equal to 0 and q equal to minus 1 and go through the procedure that we looked at in today's class, we will get C1 equal to 0 and C0 equal to 0. We are guaranteed to get that. That will tell us that x square minus 1 is essentially a factor of this, and it's because x square minus 1 is a factor of this, we will get x equal to 1 and x equal to minus 1 as the 2 solution, and the deflated polynomial p n minus 2 is going to be nothing but x minus 2. So that will lead us essentially to the 3 solutions, x equal to 1, x equal to minus 1 and x equal to 2. Okay, that was essentially about the Bayer-Stokes method. What I urge you to do is just go and read up about the Bayer-Stokes method in the second textbook that we have over here, Chapra and Canal numerical methods. So this is where essentially we end our module 4, which was on algebraic equation solving. In module 5 we will talk about interpolation and curve fitting, or what is known more technically known as regression. That is what we will cover in the next module in this course. Thank you.